If one current in the Atlantic stops, winters across northern Europe could drop by about 10 degrees, London could fall to -20, and Scandinavia could become colder than Siberia. That current has run without pause for thousands of years, and it is now the weakest it has been in 16 centuries. Scientists have just confirmed it is showing the early signs that come right before collapse. This is what that current is, why it is failing, and what happens to the world if it does. Britain sits at the same line of latitude as parts of Siberia. Norway lines up with the southern tip of Greenland, and much of Sweden runs level with the frozen coast of Hudson Bay. By the plain arithmetic of where these places sit on the globe, northern Europe should be locked in ice for half the year. It should be tundra, largely uninhabitable, capable of supporting perhaps a tenth of the people who live there now. Instead, London grows roses, Dublin rarely sees hard snow, and tens of millions of people live through winters that are merely gray and damp rather than deadly. The reason for that is not the land, it is the water. A current in the Atlantic Ocean has been quietly carrying tropical heat northward for thousands of years, and that heat is the only thing standing between northern Europe and a climate closer to central Canada's. It is so constant and so reliable that entire civilizations have been built on the unspoken assumption that it will always be there. Right now, that current is the weakest it has been in more than 1,000 years. By the longest reconstruction scientists have, it is the weakest it has been in roughly 16 centuries. And for the first time, two separate lines of evidence, one from a supercomputer, one from 30 years of satellites, point to the same conclusion. The system may be showing the early warning signs that, in every simulation we have, come just before it fails. This is the Atlantic Meridional overturning circulation. To understand why its weakening should concern you, you first have to understand what it actually is. The system begins in the Gulf of Mexico, where shallow tropical water sits at around 27 degrees Celsius. Wind pushing across the surface drives that warm water northward, up along the eastern coast of the United States, through the Straits of Florida and past North Carolina at a speed of roughly 2 to 4 miles per hour. By the time it reaches the open Atlantic, it has more than doubled in size. It is moving about 80 million cubic meters of water every second in a flow nearly 150 kilometers wide. This is the Gulf Stream, the part of the system most people have heard of. But the Gulf Stream is only the surface layer of something far larger. It is the visible top of a circulation that runs the full height of the ocean and wraps around the entire planet. As this warm water travels north, it does one thing above all else. It gives away its heat. Mile after mile, it releases the warmth it carried out of the tropics into the air above it. That heat is what keeps European winters survivable. Think of it as an underfloor heating system for an entire continent, fed by a pipe thousands of miles long that runs from the Caribbean to the coast of Norway. The amount of energy involved is almost impossible to picture, and once that warm water has surrendered its heat to the sky, it begins to do something that turns out to be the key to the entire system. It begins to sink. The water grows saltier and heavier as it cools on its long journey north. Somewhere, off the coast of Norway, it becomes so cold and so dense that it can no longer stay at the surface. So it sinks, descending thousands of meters toward the ocean floor, where it begins flowing back southward in a slow, cold river of returning water. That river moves only a few centimeters per second, creeping along the bottom of the Atlantic toward Antarctica. The water eventually reaches the Southern Ocean, where the powerful westerly winds that circle Antarctica drag the surface layer away from the continent. As that surface water is pulled aside, it draws the colder water below back up toward the light in a process called upwelling. The same motion that pulls water along behind it also pushes the water ahead of it, and so the loop feeds itself. It is a single, continuous, self-reinforcing circuit that wraps around the globe. The scale of it defies comparison. A single parcel of water takes roughly 1,000 years to complete the entire journey. And the energy this system moves is staggering, on the order of 1 petawatt of heat every single second. That is something like 50 times the total energy consumption of all human civilization combined. This one current carries close to 60% of all the heat that the world's oceans move from the tropics toward the poles. It is, by a wide margin, the most important heat distribution system on the planet, and it is held together entirely by a feedback loop. The trouble with feedback loops is that they stay stable right up until the moment they are not. Everything about this system depends on one thing: the ability of the cooling northern water to become dense enough to sink. Water draws its density from two sources. The first is temperature. Cold water is heavier than warm water because, as water cools, its molecules slow down and pack more tightly together. The second is salt. Salt water is heavier than fresh water because the dissolved salt adds mass without adding much volume. The same liter of water simply weighs more once you dissolve salt into it. The North Atlantic engine runs on water that is both cold and salty enough to sink. And that is exactly where the problem now lives. There is, in effect, a tap of ice-cold fresh water pouring into the North Atlantic, the meltwater from the Greenland ice sheet, which is currently melting faster than at any point in recorded human history. That fresh water dilutes the salt in the surface ocean. It softens the very density contrast that tells the cooling water to drop toward the bottom. That weakened contrast means the water sinks with less force. It does not descend as far or as fast, and so it drives the entire circulation with less power. For a long time, the system can absorb this. It can take in a great deal of fresh water and respond only by gradually slowing down. But that is true only up to a point, a threshold scientists call a tipping point. Beyond it, the process does not slow gently. It collapses, suddenly and almost completely. We know this can happen because it has happened before. About 12,900 years ago, near the end of the last ice age, the planet was warming quickly and the great ice sheets were in retreat. The world was on its way out of the cold. And then, very suddenly, the North Atlantic region snapped back toward near glacial conditions, as though something had thrown the climate into reverse. This event is called the Younger Dryas, and it lasted a little over 1,000 years. Temperatures around the North Atlantic fell by several degrees within decades, a fast, brutal return to the cold that was supposed to be ending. The leading explanation is a sudden, massive flood of glacial meltwater into the North Atlantic, which diluted the surface ocean and slowed or shut down the overturning circulation. It is, almost precisely, the same kind of freshwater disruption now underway around Greenland. We can read the event in the ice itself. Cores drilled from the Greenland ice sheet record the temperature swinging back toward glacial cold in a matter of decades, locked into the chemistry of the ancient snow. Whole ecosystems reorganized as it happened. Forests pulled back and tundra returned across northern lands that had only just begun to thaw. That is what makes the Younger Dryas far more than a piece of ancient history. It is the clearest evidence we have that this circulation is not permanent. It can fail. And when it fails, the change does not unfold over comfortable centuries that give people time to adapt. It arrives within a single human lifetime. The Younger Dryas tells us the collapse is real and physically possible. What it cannot tell us is how close we are to triggering another one. For decades, that second question, how close, was one scientists simply could not answer. And without an answer, the warning stayed abstract. For a long time, the honest response to the question, how close are we to the tipping point, was a simple admission. We do not know. Scientists could measure how strong the circulation was. A line of instruments strung across the Atlantic at 26 degrees north, known as the Rapid Array, has been measuring the strength of the flow directly since the year 2004. But strength on its own does not tell you how close a system is to collapse. A current can be slowly weakening and still be nowhere near its threshold. Measuring its strength is like watching a speedometer. It tells you how fast you're going, but nothing about how much fuel is left in the tank. What scientists needed was a fuel gauge, a measurement that revealed not just the speed of the circulation, but its nearness to the edge. A team at Utrecht University in the Netherlands set out to build exactly that. And their insight came from something that had been sitting quietly in the scientific literature for years, without anyone fully appreciating how important it was. It had to do with the Gulf Stream, specifically with where the Gulf Stream sits and what holds it in place, because it turns out the position of that warm surface current is not anchored from above by the winds, as you might expect. It is anchored from below. And that hidden anchor is the key to reading how healthy the whole system really is. The Gulf Stream's path is held in place by the cold return current flowing southward far beneath it, along the ocean floor. As that lower current moves past the point where the Gulf Stream peels away from the American coastline, it generates a kind of rotational force, and that force pins the Gulf Stream into its familiar position. The warm surface current and the cold current below it are locked together. This creates a clean line of logic. If the overturning circulation is weakening, then that cold lower current must be weakening too. And if it weakens, its grip on the Gulf Stream should loosen, which means the Gulf Stream should begin to drift slowly northward. The position of the Gulf Stream, in other words, should act as a visible readout of the health of the entire hidden system below it. There was just one problem. Most climate models divide the ocean into a grid of squares roughly 100 kilometers across. At that resolution, the models are too coarse to capture this behavior. They had never actually reproduced the way the lower current pins the Gulf Stream in place. The mechanism was real, but it was invisible to the very tools scientists use to study the ocean. To see it, someone would have to build a model fine enough to resolve where the Gulf Stream truly sits, and that turns out to be an extraordinarily expensive thing to do. The researchers, René van Vesten and Henk Dijkstra, decided to build that finer model. Instead of grid squares 100 kilometers across, theirs used squares just 10 kilometers across, 10 times the resolution of a standard climate model, and detailed enough, at last, to place the Gulf Stream where it actually belongs. The reason this work had not been done before is almost mundane. The relationship between resolution and computing cost is brutal. Making the grid 10 times finer makes the model roughly 1,000 times more expensive to run. If you tried to run this simulation on an ordinary laptop, you would be waiting around 14 million years for it to finish. Even on the Dutch national supercomputer, a machine called Snellius, which performs roughly 14 quadrillion calculations every second, the simulation took about 6 months of continuous running. That kind of computer time is neither cheap nor easy to secure, and climate research at this scale is chronically underfunded. Part of the reason a question this important went unanswered for as long as it did. Once they had that high-resolution ocean, the team did something deliberately simple. They began adding fresh water to the North Atlantic at a slowly increasing rate, simulating the growing flood of meltwater coming off Greenland. And then they watched. They let the model run forward, and they observed what the circulation did as the fresh water kept arriving. What unfolded happened in 2 very distinct stages, and the difference between those 2 stages is the most important part of this entire story. In the first stage, which played out over roughly 400 simulated years, the Gulf Stream drifted gradually northward. By the end of those 4 centuries, it had moved about 133 kilometers from where it began. It was slow, it was steady. It was the kind of change you would never notice if you were not specifically looking for it. This was the early warning phase, the circulation weakening but still holding in something close to its stable state. Then came the second stage, running the simulation forward over just 2 additional years, not centuries, years. The Gulf Stream lurched northward by about 219 kilometers. It moved farther in 2 years than it had in the previous 400. At this point, the lower circulation had changed so quickly that it lost its ability to hold the Gulf Stream in place. The anchor let go, and as it did, the entire overturning circulation came apart. Sit with the proportions of that for a moment. What took 400 years in the first stage took only 2 years in the second. The system gave almost no warning at the threshold itself. It drifted and drifted and drifted. And then it broke all at once. This is the defining danger of a tipping point. The long, slow approach looks deceptively gentle, and the collapse, when it finally comes, is nearly instantaneous by comparison, which raises the only question that really matters. Where, in that sequence, are we right now? We cannot measure the full overturning circulation continuously, because monitoring the cold lower currents across an entire ocean in real time is extraordinarily difficult and expensive. But we can measure the one thing the model told us to watch. We can track the surface position of the Gulf Stream from space using satellites in something close to real time. So after establishing this 2-stage pattern in the model, the team went looking for it in the real world. They turned to satellite measurements of sea level going back to 1993 and to measurements of temperature beneath the surface going back to 1965. Both data sets showed the same thing, a statistically significant northward drift of the Gulf Stream on the order of 50 kilometers over the past 30 years. The Gulf Stream is now sitting almost exactly where the model's first stage says it should be. That tells us something sobering and specific. We are, at the very least, already inside stage 1. The harder question is how far through stage 1 we have come, and that is where the honest uncertainty lives. In the model, stage 1 ends roughly 25 years before the full collapse, but that figure carries enormous uncertainty. The real ocean is being pushed by warming, by shifting winds, by changing rainfall, and by Greenland's melt all at once, while the model was deliberately kept simple. The true window could be longer. It could also be shorter. What this research delivers is not a countdown. It is something arguably more valuable, a mechanism and a signal we can finally read. Suppose the circulation does cross that threshold. What actually happens? Begin with Europe, which loses the heat the current has delivered for thousands of years. Average winter temperatures across the northern half of the continent could fall by around 10 degrees Celsius. Sea ice, now confined to the Arctic, would begin creeping south toward the coastlines of Britain and northern Europe. London could see winter lows near -20. Scandinavia could become colder than Siberia. The growing seasons that have fed the continent for centuries would, in many places, simply stop functioning. The damage would not stop at Europe. As the North Atlantic cools, the planet's tropical rain belts would shift southward. The monsoon systems that deliver seasonal rain to West Africa and South Asia would weaken and move, disrupting the water supply and the harvests of well over 1 billion people. A current in the Atlantic, failing, would reach into the food security of farmers thousands of miles away who have never once heard its name. And there is a quieter blow beneath the surface. The overturning circulation drives the upwelling that lifts cold, nutrient-bearing water toward the sunlit top of the ocean. Remove it, and those surface waters begin to starve. The phytoplankton that feed on those nutrients are the base of nearly the entire marine food web, which means their collapse would ripple upward through fisheries that feed a large share of humanity. This is the full weight of what the Gulf Stream's quiet northward drift is pointing toward. The question is what we choose to do with a warning we can now, at last, actually see. Human beings are remarkably good at understanding one kind of gamble and remarkably bad at understanding another. We instinctively grasp asymmetric upside, the small bet with the enormous payoff, the lottery ticket, the lucky break, the tiny investment in what turns out to be the next great company. That kind of long shot excites us, and we organize a great deal of our thinking around it. What we are far worse at is the mirror image, asymmetric downside, where a small change in behavior now could prevent a catastrophe later. We struggle to feel the weight of a disaster we have never personally lived through. Consider that a surprising share of homeowners decline to insure their homes against fire or flood, even knowing those things happen to someone every day. Now scale that same blind spot up to an entire planet. None of us has ever had to pay for the climate we inherited, and none of us has ever witnessed a globally significant event like the failure of this circulation, because it has not happened within recorded human history. There is an idea in cosmology called the Great Filter, the notion that somewhere in the development of any civilization sits a barrier that most do not survive. We tend to imagine it as something cinematic, an asteroid, a war, a sudden catastrophe loud enough to demand an immediate response. It may be far more likely that the real filter is a quiet one. Civilizations may not fail because they miss the dramatic threats. They may fail because they normalize the slow ones. We have known this circulation was weakening for over a century. We have had satellites watching the Gulf Stream drift for 30 years. The signal was there the entire time, hiding in plain sight, inside data we were already collecting. We simply did not know what we were looking at. Now we do. Whether that knowledge has arrived early enough to matter, or already too late, is the one part of this we do not get to model in advance. We only get to live through it. And it leaves a single, uncomfortable question hanging in the air. What else are we missing?